We will now discuss the interaction between electromagnetic radiation and matter in terms of classical physics, which provides valuable insight even though the classical description cannot explain all aspects. Our classical model is a mass on a spring that is subjected to an oscillating driving force and to damping, which is another word for friction. We will apply this model to describe the interaction between electromagnetic radiation and matter when we discuss the different spectroscopic methods in the following lectures. Then it will be important to identify what is the driving force and what corresponds to the mass on a spring. In most cases, the driving force corresponds to the electric field of the radiation and the mass to the electrons or to the nuclei in the interacting molecules. When a spring with attached mass is extended and released, it will oscillate at its intrinsic angular frequency ω0, which is determined by the spring force constant. However, when it is driven by a driving force, indicated here, that oscillates with the angular frequency ω, the spring will eventually oscillate with the same frequency as the driving force. This is shown on the left-hand side. The driving force is depicted as a cosine function in green. The black curve is the oscillation of the spring. It is also described by a sinusoidal function with the same frequency ω as the driving force. Note, however, that the spring movement lags behind the driving force. This happens when there is friction between the mass and its surrounding, which corresponds in spectroscopy to interaction between atoms and the environment. One says that there is a phase difference between the movement of the driving force and that of the spring. The phase delay occurs because resistance due to friction has to be overcome. Such a phase-delayed cosine function is mathematically equivalent to the addition of a cosine and a sinus function. The cosine function on top is in phase with the driving force and represents the in-phase component of the movement. The sinus function on the bottom lags behind the driving force by 90 degrees and therefore represents the 90 degrees out of phase component of the movement. Note that the in-phase component can also be 180 degrees out of phase when its amplitude has a different sign than that of the driving force. We switch back to the previous slide and discuss now the amplitudes of the two components, as these depend on the driving frequency and on the intrinsic frequency of the spring. We can see that the in-phase amplitude is positive at low frequencies, is 0 when the driving force is equal to the intrinsic frequency, and turns negative when the driving force frequency is larger than the intrinsic frequency. The 90 degrees out of phase amplitude is small when the driving force frequency is very different from the intrinsic frequency. However, it is maximum when both frequencies are equal. We will continue discussing these two curves for a moment. It turns out that the curve for the in-phase movement, the gray curve, describes a phenomenon called dispersion, which is the frequency dependence of the refractive index. We will not discuss it further, but instead focus on the curve of the 90 degrees out of phase component. The enhancement of the amplitude when the driving force is near the intrinsic frequency can be quite dramatic. It is only possible by energy transfer from the driving force to the spring, and it turns out that the energy absorbed by the spring is largest when the two frequencies match. Such a phenomenon is called resonance. It gives evidence for the absorption of energy by the spring from the driving force. In spectroscopy, this corresponds to energy absorbed by the atoms or molecules from the electromagnetic radiation. We will return to the orange curve shortly, but summarize the main conclusion so far. The simple mass on a spring model describes the interaction between electromagnetic radiation and atoms or molecules. In particular, the 90 degrees out of phase movement shows a resonance phenomenon that we also find when electromagnetic radiation is absorbed by atoms or molecules. I could go on now and continue straight with a discussion of the mathematical formula for the orange curve, but often it is beneficial to stop and ask the question, does it make sense? The reward for this effort is often a deeper understanding of the topic. So we ask, does it make sense? In particular, I want to think about three questions. Why is the amplitude in phase at low driving force frequency omega? Why is the amplitude 100 degrees out of phase at high driving force frequency omega? Why is the amplitude largest when it is 90 degrees out of phase with the driving force and when omega equals omega 0? In order to answer these questions, I want to remind you of some properties of oscillating movements. When the amplitude of the movement of the mass is described by a sinus function, the velocity of the mass is described by a cosine function, and its acceleration by a minus sinus function. When the spring is not subjected to an external force, then the acceleration is caused by the restoring force of the spring. Therefore, acceleration and restoring force are proportional. We check again, does this make sense? And look at two particular displacements of the mass. The first one is the upper turning point, when the spring is most contracted. The amplitude has its most positive value. At the turning point, the velocity is 0 and the acceleration negative. That is, it points down. The reason for this is the restoring force, which wants to bring back the spring to its equilibrium length and therefore points down to expand the spring. We next look at the situation when the spring passes through its equilibrium position. Here, the amplitude is 0, as there is no deviation from the equilibrium length. At the same time, the velocity has its largest negative value. That is, the movement is fast and downwards. The acceleration is 0, as there is no deviation from the equilibrium length and therefore no restoring force. Now we start to answer the first question. Why is the amplitude in phase at low driving force frequency omega? When the amplitude is in phase with the driving force, then the driving force is 100 degrees out of phase with the acceleration and with the restoring force of the spring. Therefore, both forces oppose each other and partially cancel each other. The resulting force is small and therefore the resulting acceleration also. This slow acceleration can only produce a slow oscillation. In other words, slow oscillations require that the total force acting on the mass is small, and this is the case when the oscillation amplitude is in phase with the driving force. The next question is, why is the amplitude 100 degrees out of phase at high driving force frequency omega? When this is the case, then the driving force is in phase with the acceleration, that is, with the spring restoring force. Both forces work now together, and the resulting force and the resulting acceleration are large. This gives a fast oscillation. The final question is, why is the amplitude largest when it is 90 degrees out of phase with the driving force and when omega equals omega 0? The 90 degrees out of phase amplitude lags behind the driving force. Thus, the driving force is in phase with the velocity of the mass. It generates the strongest acceleration when the velocity is highest. The maximum velocity increases and therefore also the amplitude of the oscillation. Because the intrinsic frequency of the spring and the frequency of the driving force are the same, the driving force tends to increase the velocity throughout the entire oscillation. The only exceptions are the turning points where velocity and force are zero. Eventually, this would lead to an infinite amplitude, but because there is always friction opposing the movement, the amplitude stays finite. Speaking about friction, friction is also a force that is proportional to velocity, but it is always directed against the velocity. If a spring is extended and oscillates freely, but is subjected to friction, then the oscillation amplitude decreases with time. This is just the opposite of what we just discussed for the driven oscillator. When the driving force has the same direction as the velocity at all times, then the amplitude of the oscillation increases. We will now turn back to the curve that describes the amplitude of the 90 degrees out of phase movement. This curve is a Lorentzian function as given here. As already mentioned, it describes also the shape of absorption bands in the spectrum of the absorbed electromagnetic radiation, and therefore it is also called Lorentzian line shape. The amplitude is given by tau divided by 1 plus the squared difference between omega and omega 0 multiplied with tau squared. In this equation, omega is the angular frequency of the driving force. In spectroscopy, the driving force is often the electric field. Omega 0 is the intrinsic angular frequency of the mass on the spring in the absence of driving force. Tau is the relaxation time. The name relaxation time stems from the properties of the system in the absence of an external oscillating driving force. When the spring is extended and then released, it undergoes oscillations which decrease in amplitude with time because of friction. This is called relaxation back to the equilibrium position. The decay time tau for the oscillation amplitude is called relaxation time. It depends on the friction, because strong friction leads to a fast decay. In spectroscopy, tau is related to the lifetime of excited states. When the lifetime is short, an excited state will quickly return to the ground state. One says then that the relaxation time is short. This is the case when there are strong interactions with the environment. The interpretation of the curve is as follows. The amplitude of the oscillation that is 90 degrees out of phase with the driving force as maximal when the frequency of the driving force matches the intrinsic or natural frequency of the mass on a spring. That means that most energy is absorbed close to the intrinsic frequency. The width of the Lorenz curve is inversely proportional to the relaxation time tau. Much friction or strong interactions with the environment give broad bands, but little friction or weak interactions with the environment give narrow bands. In other words, a short relaxation time produces broad absorption bands in spectroscopy and in the mass on a spring system.